So we proved yesterday the upper bound. So now we turn to the lower bound. And so we introduced yesterday a new dynamics, which is if I fix a function g. So let's assume that this function g now depends on time, just for fun. And so this is a new generator, which will be given by so we have seen that we have here exponential minus gx plus e minus gx, eta x plus e minus eta x. And now, and this is multiplying f sigma x, x plus e eta minus f. Okay, so f of eta. So this is a generator which appeared naturally because when proving the upper bounds, we introduced certain martingales, the exponential martingales, and we have seen that actually these exponential martingales are modifying the dynamics, turning the exclusion to be a weakly asymmetric exclusion. So we would like to investigate these new dynamics. And my claim is that, well, under this new dynamics, the empirical measure will evolve according to a new equation, which is this equation in which we introduce a perturbation, which is 2 times the gradient of sigma of u, the gradient of g. Okay, and this is what I want to show you. And the way in which we show, we just write down a martingale. So you fix a test function h, say that belongs to C2. You define a martingale mh of t, which is pi t h minus pi 0 h minus 0t, and then now you apply this generator to pi and sh ds, and this is speed up by n squared. So what I claim, and I won't check that, is that this martingale converges to 0, because if you compute its square, you take its expectation, this is converging to 0. So the way in which you prove that is just by computing gamma. Okay? And you compute gamma and you check that gamma is of order 1 over n. So now I just want to compute this martingale, which means I want to compute this term with the n square. So I have n square and Lg. So Lg is given by this expression. So I have a sum over x. And here I have exponential minus gx plus e minus gx, eta x plus e minus eta x. And now this is multiplied by this function computed at the configuration sigma x, x plus e, eta, minus the same expression at eta. So let me first compute the expression which is inside braces. So over there I have 1 over n, the sum over y, and hy sigma x, x plus e, eta at y minus eta at y. Okay, so this is the first term, and minus eta y comes from the second one. Now this is 1 over n. So again, you see that for y different from x and x plus e, this is 0. So there is just 2 terms. the first term it's y equal to x. If y is equal to x, then this becomes eta x plus e, and this one x, and then plus y equal to x plus e, and now this is eta x, and this is eta x plus e. Okay, and therefore this is, we have seen this term many, many times. This is minus hx plus e minus hx times eta x plus e minus eta x. Okay, so this is the expression which appears here inside brace. So I'll just rewrite so that this expression, it's equal, we have a minus and 1 over n, so that becomes minus n. And now we have exponential minus gx plus e minus gx, eta x plus e minus eta x, times this expression, which is hx plus e minus hx, eta x plus e minus eta x. Right? So this is a term of order 1 over n. So I will start with an expansion of this one. So there is first a term. So this is a term of order 1 over n. So I have first 1. Right? So a term of order 1 over n, which is minus gx plus e minus gx times eta x plus e minus eta x. And then there's another term here which will be order 1 over n squared. But this 1 over n squared with this 1 over n will give me 1 over n cubed. I have here n squared, so this is small. Okay, so I can just stop my expansion here at 1. So I'll stop my expansion at 1. Then let me take 1. So 1, it's multiplying this term. And this one, we have seen it also many, many times. So this is the first term, and then we have a second term in which we have minus with minus, so that's plus n. And in this term, I have gx plus e minus gx, hx plus e minus hx, and then the square. Okay. So here, you remember what we do is we integrate it by parts, and that gives me eta x times the Laplacian of h at x, the discrete Laplacian. So I multiply that by n squared to get it, the discrete Laplacian here, so I have to divide it by n squared. Okay. So this Laplacian includes n squared, so it's n squared times the difference, so it's order 1. So this is the first term, and then, well, this term it's order 1 over n, this one 1 over n, so that's equal to 1 plus n x. So here I have gradient j, g, gradient h, and this term. So again, this term, it's not a function of the empirical measure, but we know how to replace it. We will replace it, well, it's exactly the same function which appeared yesterday. So its expectation, it's equal to 2 times sigma of alpha. So I will replace that by 2 times sigma of eta epsilon n x, okay, which is the average on the size on the box of size epsilon around x. So this is what we get, and therefore, if I come back to the martingale. The martingale converges to 0. So this tells me that, and if I remember that pi in the limit, pi it's absolutely continuous, and I represent by u its density, what I get is that 0 it's equal to the integral on the torus of u tx hx minus the integral on the torus of u 0x hx, and now minus this quantity. So this quantity, this is the second derivative of h integrated with respect to the empirical measure. So this is the integral from 0 to t ds, the integral over the torus of u sx Laplacian of h. So this is the first term, and then I have plus 2 times the integral from 0 to t ds, the integral on the torus dx, and there I have, well, the derivative of g, derivative of h, sigma of u. Okay? So if I integrate it twice by part, I get this Laplacian here. So let me do that. This comes by integrating twice, because we are on the torus with periodic boundary condition. So now let me integrate it once, this gradient. So this one I will write. I integrate it once, so I get a minus sign. And here, by integrating, what I get is gradient of sigma u gradient g times h. All right? So this is what I get. And from this equation, so if I take time derivative in this equation, what I get is, so that's formal, that will disappear. Here, this integral will disappear, as well as this one. And what I get, since this is true for all h, it means that dtu, it's equal, this is 0, so let me put that on the left-hand side. So this is equal to Laplacian u, because I have a minus sign here. Here I have a minus. Yeah, but this is minus. Sorry, it's a minus for everything. Okay. I messed up the minus sign. I have a minus here. Okay, so it's minus everything. And so I have to put inside these two terms. So this one with a minus and this one with a plus. Okay. Sorry, this one with a plus and this one with a plus. So both have pluses, but now I integrate by parts. So this is still plus, but this one it's a minus. With that minus, it becomes a plus. So in the other side, it will become a minus. So minus 2 times gradient sigma of u gradient of g. Okay, and this is exactly what I told you. Okay, so this is the hydrodynamic equation. All right, so for this generator, if you repeat what we did for the exclusion with speed change, in which you have to do the replacement lemma, you can prove exactly as the way we did that the hydrodynamic equation is given by that, so that the empirical measure will converge to the unique solution of this equation. Of course, you need to prove that this equation has a unique solution, which is another problem. Okay, but this is okay. So this is what we get. So that's the first point. first important point in the proof. So once I have that, I can prove very easily a lower bound. I'll just close my eyes and repeat exactly the argument I presented for IID random variables. Right? So I want to estimate the probability that pi n belongs to some open set G. G is a subset of the set of trajectories. Okay, so it's a subset of trajectories. So let me fix some u which belongs to G. So u, it's an element here. Okay, so it's a trajectory. So actually, pi, it's an element here, and I'm assuming that pi t dx, it's equal to u tx dx. And more than that, I will be assuming that u, it's very nice. U, it's nice. What it means for me that u, it's nice, it means that u, it's smooth. So let's say that it belongs to C12. And that it's bounded below and above 0 and 1. Okay, why? Okay, I could ask much more, but why I'm asking that? For the following reason. Okay, so u I fixed. U, it's very nice. So here's u. Now I look at this equation. Well, since u belongs to C12, this is continuous. Laplacian, it's continuous. So this equation, I will write it as dtu minus Laplacian u. It's equal to minus 2 sigma of u gradient of g. So I'll fix a time t. And I will consider this equation. Okay. Well, I can solve this. I can find. Sorry, there is a gradient here. I can solve this equation to find g. Okay. I fixed u, a nice u. Now, given that u, for each t, I find a solution for this equation. Okay. That's well, and you can, how do you prove that? How do you solve that? Well, you integrate it once. You divide that by sigma. You integrate it again, and you get g. Okay? Just have to be careful because you want g to be periodic. And so you have to add constants for these integrals to be 0. Okay? But what I claim is that given u smooth, there exists g. And why did I ask u to be between delta and 1 minus delta? Because sigma of u, if you remember, it's u times 1 minus u. So if u it's between delta and 1 minus delta, sigma it's between delta prime and 1 minus delta prime. So it's not 0, and therefore I can divide. Just to make sure that there exists a solution g for that. So for each g, for each time, I find a gt, and therefore what I have, it's a function which depends on t and x. Okay, and if u, it's very nice, it's smooth, then G also is smooth. Okay? So this function G, which I just obtained, I can show that it belongs to C10 0tx time t. Okay, I don't prove it to you, but you see that, well, G will get, it's more regular than these functions. Because, well, the second derivative of G is equal to that. Okay, so it's smoother than that. That's fine. So you gave me U, I constructed G. Okay. Now I proceed as follows. I want to estimate what is the probability that my pi n belongs to G. That's horrible. So let's call this set A. Okay, so A, it's an open set, and G, it's a function. Okay, so now this is certainly larger than the probability that pi n belongs to a ball of size epsilon around U. Okay, so you take a tube of size epsilon around U. Since A, it's an open set, I can find the neighborhood of U, which it's contained in A, because A is an open set. Now, I rewrite this as PG dP dPG of the indicator that pi n belongs to B epsilon U. So now I changed my measure with this G, which I just constructed, because now, since G is the solution of this equation, it means that under this new measure, the empirical measure will evolve according to this equation. But this equation, it's exactly the equation which is satisfied by U. So the empirical measure, it's converging to U. Okay? And this is why I constructed G, and then I inserted G. So I changed my measure in order to have a new measure, which makes U a typical trajectory. Because now, under this measure, the empirical measure is converging to the unique solution of this equation, but U, it's exactly the unique solution of this equation. Because U, it's a solution, and if this equation has a unique solution, U is the unique solution. Okay? So this is the...
Here you are using that the solution of the equation is a profile whose measure is A.
No. No. I have my set A. So now take a smooth trajectory in A. This is U. So take U in A. No? Okay? So you fix that U. Now, you consider this equation. U, it's given. You solve this equation in G. You find G. You plug G. So now, under this measure, PG, the empirical measure converges to the solution of this equation. So let me write, there are too many U's. It converges to the solution of this equation. Okay? But who is the solution of this equation? It is U. So pi is converging to U. Okay, so we are going exactly in the upper bound. When proving the upper bound, we introduce these measures. Okay, so we study these measures. What are the law of large number for these measures? The law of large number of these measures are given by these equations. Okay, so let's keep that in mind. Now I'm proving the lower bound. And I take a trajectory in A. And knowing that, I find G, which solves this. I put G here, and then I get what I want. So this event under G has measure 1. Yeah, I need the uniqueness. Okay. So that's first point. But okay, that's the crucial point of the proof of the lower bound. Now what you do? I know I computed already this I computed already this Radon-Nikodym derivative, right? So it was pi n g times t times n minus the same thing times 0 minus here I had this exponential minus and so on. Okay, well, okay, maybe I'll write it. So this was the Radon-Nikodym derivative, right? So actually we started with this exponential, and this is how we defined PG. Okay? We computed this expression, and we proved that this expression, so that this is n pi n gt minus n pi n 0g. And here, after a long computation, this was minus 0t pi ns Laplacian of g ds, and minus, maybe I had a 2. Yeah, I think I had a 2. Sigma of u gradient g squared ds. Plus some errors, but which were small. Okay? So when we computed that, we had to do a replacement lemma to replace a function like eta e minus eta 0 squared by a function of the empirical measure. Okay? But modulo some small errors, this is the formula for the empirical measure. So here we have one of the empirical measure. So this minus 1 is just with a minus sign here in front. And here I have an n in my, and there is an integral of space. Okay, so this is the formula for Pg, the Radon-Nikodym derivative. So 1 over this Radon-Nikodym derivative is just to put a minus sign here. Now, so here is the formula which I have here. Okay, but now I know that pi n belongs to this ball. So pi n, it's very close to u. So in this equation here, I can replace pi n by u by paying a small price, an epsilon price. And so this is equal. Mind that this, it's exactly what we did in the large deviations for IID random variables, right? We had the formula for the martingale, and since xn bar was close to beta, we replaced xn bar by beta in the formula for the martingale. So here, so this is n, so let me put n in front, and so this becomes ut x g, okay, gtx minus u0x g0x, and since I'm taking, there is an extra term here which I didn't write because g here, I'm assuming it to depend on time, so there is an extra term which is usx dsg, and then these terms minus the us Laplacian of g and minus sigma of u greater than g squared. Okay, so this is once I replace pi by u. Okay, so I am placing, and this was pi n, so this is, let's say, pi. Okay, I had here a function of the empirical measure, but now the empirical measure is close to u, so I can replace everywhere the empirical measure by u by paying a small price. If it is too sketchy, just ask questions. Let me interrupt, complain. So once I have in this Radon-Nikodym derivative replaced pi by u, this is a number, it doesn't depend anymore on pi, so I can move it out from the expectation. And in the expectation, I have something which is converging to 1, because without this expression which I removed from the expectation, I have the probability under G that pi n belongs to this neighborhood, but this is converging to 1. So when I take 1 over n log of this probability, I will have 1 over n log of this probability. Bon, this is larger or equal than 1 over n log of an expression which converges to 1. So that will vanish, plus 1 over n log of this exponential. And when I take log and then I divide it by n, this is converging to that expression. So in conclusion, what I would have proved is that 1 over n log the probability that pi belongs to A, it's the limit imp, it's larger or equal than this expression. So this is the integral of u at time t x gtx minus u0x g0x minus the integral from 0 to t of dsg usx dx I have a minus sign in front of everything, and then minus these terms, minus 0t, t, u Laplacian g minus sigma of u greater than g squared. Okay? And if I can prove that this is equal to I of u, I would have proved the lower bound for u. So I still have to prove that I, remember, I was given by a variational formula, was a soup over all g, all h of something. What I claim is that I of u is equal to this expression. But this I have to show. And if I can show that, then I would have proved that the limit of pi 8 bounded by that. But mind that I proved that only for very special trajectories u. Okay, I started here at the beginning saying, well, let's take a u which is smooth, bounded away from 0 and 1. Because for that u, I can construct a g. So if everything, okay, what we proved at the end is that, let me optimize this inequality over all such u. So that will entail that the limit inf of 1 over n log of the probability that pi n belongs to A, it's larger or equal. So I will have a soup here because I'm optimizing, but with a minus it turns out to be an inf I of u. But these u are in A intersection, let me call that R, where R is the set of very nice trajectories. So trajectories for which there exists a delta such that u is bounded between delta and 1 minus delta, and such that u is C1, 2. This is not exactly what we want, right? What we want is to remove this R. So there is a technical step which is this one. So let me take, I want to say that this is actually equal to the minus the infimum over all u in A of I of u. Okay? So let me take I of, if I of u, of all I of u are infinite, okay, here in this infimum, I can restrict my attention to all u's for which I of u is finite. Because if I of u is equal to minus infinity, there is nothing to do. It's equal to plus infinity, there is nothing to do. Okay, if I of u is plus infinity, I won't consider here in this infimum. If everyone is equal to plus infinity, then I don't care because this inequality is trivial. Because I want to show that something is larger or equal than minus infinity. Okay? So I can consider in this infimum only the u's for which I of u is finite. So now take a u such that I of u is finite. What I have to prove, so this is a theorem which I have to prove, is that there exists a sequence un which belongs to R. So R is the set for which all these things happen. So u is bounded away, u is smooth. There is a un which belongs to R such that un converge to u and I of un converge to I of u. Okay? Because what I want to prove is that the limit imp of 1 over n log of pi nu pi n belongs to A, it's less or equal than minus the infimum of this. Okay? For that, it's enough to prove that this holds for all u in A, such that I of u, it's finite. Okay? If I can prove that this inequality holds for all u in A with I of u finite, I can optimize. I'll get here the infimum over all u in A, and I can remove this restriction as I said. So this is what I need to prove. What I can prove is that this is larger or equal than minus I of w if w belongs to A and R. Okay? But now fix a u in A for which that holds. Okay? From this theorem, I know that there is a sequence un which converge to u and such that I of un converge to u. Since un converge to u belongs to A is an open set. This means that there exists n sufficiently large for which un belongs to A if n is larger than n0. Okay? Un is converging to u. A, it's an open set. So there exists one starting from which everyone is in A. Okay? So for all these UNs in A, I can prove this. Because now UN is smooth and it belongs to A. From the first part of the proof, I can do that. And now if UN converge, since IUN converge to I of u, this guy is converging to that, so I have this bound. Okay? So what we just proved is that if you're able to prove the lower bound for a subfamily of trajectories, in order to complete the proof of the lower bound, you need to show this theorem. Okay? So this theorem is called the I density of the rate function. I, it's called the rate function. This theorem, it's called the I density. And this is usually the most technical part of the proof of the lower bound. Usually it's very easy to prove this bound for smooth functions, u. Just repeat what I did. But then you have to show that you can approximate any trajectory by smooth trajectories in such a way that I also converge. And this is model depending. I mean, for each model, you have to prove that this theorem holds. All right? So that's an extremely important step in the proof of the lower bound. And to complete my argument, what I have to show is that I of u is given by this formula. Okay? I introduced I as a supremum over test functions. Now I'm claiming that I is equal to this expression. Mind that this was exactly what happened in the IID random variables, right? For the upper bound, we obtained the rate function as a soup, as a variational problem. And then we solved this variational problem. And in the lower bound, well, we get exactly the expression that we had for the upper bound, but when we change the problem, the variational problem into, when we computed the variational problem. So questions? So now what I will do is to prove that I is equal to that. So I'll recall the formula for I, and I will prove that indeed So I'm taking U as smooth. So U, it's everything you want. And I of U was given by the supremum over all functions H of pi, okay, ut ht minus u0 h0 minus, okay, let's yes, minus. So instead of writing the space integral, let me just write the brackets. So this represents the scalar product between ut and ht in L2. So this is the variational formula we obtained for the upper bound for I. Okay, this is the soup. Fine. Okay. So as a function of h, I have a piece which is linear. All terms are linear, but this one, which is quadratic with a minus sign, so this one, it's a convex function with that minus a concave, and we are taking the supremum. So the supremum will happen at the critical point. So if now I call, so what is the equation for the critical point? You take h plus epsilon times j, and you send, so you write down this expression, and you send epsilon to 0 to get that. So if g, let's say that g is the function which minimizes this expression, so g it's a critical point. Okay. So what I'm doing is that I'm writing this supremum as a supremum of a linear function which depends on u of h, okay, minus the time integral of sigma of u dh square. Okay, so I have here a linear function, which is the first four terms, and then this quadratic function. And I'm taking here. So if h is the one which maximizes this expression, this means that for all function j, the limit as epsilon goes to 0 of Lu h plus epsilon j minus that this limit is equal to 0 for all j. Right? So this is saying that if there is one which maximizes, it has to satisfy this equation. Divided by epsilon, you're right. Okay? So you're just saying that the derivative along a function j, it's equal to 0. So you see that since L of u it's linear, this means that Lu of j, and then you, okay, here it's a minus of everything here. Now you have to compute this one minus this one. Well, but that's very easy because if you expand this square, the gradient h square will cancel. There is a linear term in epsilon, and then an epsilon square term. So the epsilon square will vanish when you send epsilon to 0. So just this cross term here will be important, and the cross term will give you minus 2 times 0t of sigma u dh dj. Okay? So this is the derivative. This is this limit. This limit has to be equal to 0. So what we get is that if h maximizes this supremum, then it has to satisfy this equation. Okay? And what is this equation? Well, let's remind what is L of u. It's written here. This means that for all j, ut gt minus u0 j0 minus the integral of us ds js minus the integral of us Laplacian of j minus 2 times the integral from 0 to t of sigma u s dhs dgs, that this is equal to 0. Okay? And what it means? Well, it means, since this is true for all j, this means that dtu, it's equal to Laplacian u minus 2 times the gradient of sigma u gradient h. Okay, so it's again just integrated by parts here, that you get the derivative in u here. The boundary conditions will get out when you integrate by parts. And so this tells you that the time derivative of u integrated in space and in time with respect to j, it's equal to that. This is true for all j. Here you can integrate by part to get the Laplacian here. Here you integrate by part to get the gradient of, here, to get the gradient of sigma gradient of h, which is that, and this has to be equal to 0 because that's true for all j. Okay? So if h is the one which maximizes, it means that it satisfies this equation. Do you agree? Okay, integrate by parts here. So if you integrate by parts here, this term I'm integrating by parts in time. So I'll get this minus will become a plus. Here I have d as u, and here j. And the boundary terms will be u, j at time t. With a minus, we'll cancel this. Minus u, j at time 0, we'll cancel that one, so that one will remain. Here, integrate twice by parts, you get that. Here, integrate once by parts, you get plus gradient sigma of u, gradient h, g. Well, but this is true for all g, which means that this expression minus Laplacian of u plus 2 times this expression is equal to 0. And this is what I wrote. All right? So this is the one which maximize. Okay. U, it's fixed. Yeah.
So the minus sign that you have in front on the back of the first integral is affecting the
This one,
or just the first one?
this one, which one?
No, the second line, the first minus.
The second line, this one, the first minus.
First minus. That is affecting the two integrals or just the first one?
Just the first one. Let me see. Let's check here in this. Yeah, so I have a minus here and a minus here. So this minus, it's affecting just the first one. So here I have a minus 2. But when I integrate by parts once, it becomes a plus, while here I integrate by parts twice, so it's still a minus. Okay? And so it's minus plus, but so this is equal to 0. When I put it in the other side, I get plus minus. Okay? So H, so fixed U, for a fixed U, I found what is the H which maximize, is this one. Okay? Which means that what is I? I, it's given by this formula, by this soup. But now I found the H which maximize. So I, it's equal to the same formula without this soup, provided I place here the H. Which H? Well, the one which is given by this equation. This is the equation for H. Okay? So I obtained an explicit formula for I. I, it's equal to this expression without the soup, provided I choose H by this equation. Okay? So you give me U, I solve this equation in H, I find this H, and I plug it in this expression, and I get I of U. And this is exactly what's written there. Okay? Because there, I started with U, I solved exactly this equation, and I obtained G, and I plug it in this equation. So this is indeed I of U. Okay? Right? So how did I start the proof of the lower bound? I fixed U, and I solved this equation. I obtained G. So I changed my measure with G. I computed the lower bound, and I found that the lower bound, I found this expression for the lower bound. Okay, but this is exactly I of U, because how what is I of u? It's given by this variational formula. But I found the h which maximize this expression. It's exactly the g which I obtained over there, because h and g satisfy the same equation. All right? And that completes the proof of the lower bound, provided I proved the theorem which I raised here, which is a big technical problem. So let me just, okay, so that completes the proof of the lower bound. I just want to make a remark about the rate function. I obtained this equation. Okay, questions about this? Can I erase? You all agree? Okay, so let's go back here. In the proof of this argument, I showed that this linear function of u, it's given by this expression. So I obtained a representation of my linear function. The linear function L of u, which appears in this expression, which appears in my I. So remember, this is I of u. This linear function, it's written by this expression. Okay? So I will just replace Lu of h by, so to distinguish between this h and that h, let me call this h0. So h0 is the solution of this equation. Okay? So if you fix me u, I obtain the h which maximize is the solution of this equation. And if you give me the h which maximize, then I have this representation for L of u, right? Because I just computed that and I obtained this expression for all j. So let me write it here. Okay, so let me go back to what we were doing. I have this formula for I. So I introduced this linear functional. So with this linear function, I can write my rate function in terms of this simpler variational problem. And I was looking for an equation for h. So I said, well, if h maximize this variational problem, it means that if I take the partial derivatives in all directions, it's 0. So I got this equation for h. And this equation is equivalent to this equation. So I say, well, what is h has to satisfy this equation, which means that h satisfies this equation. Okay? So let's call me h, which satisfies this equation, h0, or hu. Okay? U is fixed. You found h of u, which is the solution of this equation. So this means that this h satisfies this. Now, what I read from this equation is that I have a formula for this linear operator. Lu of j, it's given by this expression. Remember that Lu was something completely different. Was this minus this minus this minus this. But now I just proved that actually I can represent my linear functional as this scalar product. So I will replace L of u by this scalar product in this variational formula. So actually, I of u is also equal to the supremum over all, h we have there, of L0 of Lu of h, but Lu of h, it's now this expression. So it's 2 times the integral from 0 to t of sigma of u dhu dh minus the integral from 0 to t of sigma of u dh squared. All right? Okay? And, well, okay. So what I get from this is that this supremum, it's also equal. So I want here to complete the square, because I have gradient h squared, 2 times gradient of hu gradient h. So I'll just complete the square. I will add and subtract sigma of u dhu square. Yeah. I did it, but you left the room. So I did that, and I just replaced in this formula h by hu. And by replacing this formula by h of u, I concluded that what I had here before was exactly I of u. Okay? I'm getting a new formula for I of u. So the new formula for I of u, I just add and subtracted this expression. Okay? Now, I have the minus sign I will keep. The plus sign, well, this does not depend on h, so it can get out from the supremum. So this is equal to 0t sigma of u gradient hu square ds. Okay? And then remained the minus. So I have minus this expression, minus this one, plus this one. So this is minus 0t sigma of u dh minus dhu square ds. Okay? I just completed the square. So this is what I get. And now you see that this supremum, this is positive. With a sign, it's negative. So it's always negative. And when I approximate this guy by h, I get 0. So this supremum is 0, which means that I have this formula also for I of u. Okay? What is I of u? I have 2 formulas, 2 different formulas. The one I gave you, in which you just replace h by h of u in that expression. And here is another formula for I. How you get it? Well, I give you u. You solve this equation. You get h of u. You plug h of u here. and you have your formula for I. Okay? And what is gradient of u? So dtu minus Laplacian, it's equal to 2 times minus 2 times the gradient of sigma u gradient of u. So let me divide that. Let me take the inverse of this expression on both sides. So that will cancel here. And I get that gradient of hu is actually minus 1 over 2 sigma of u gradient minus 1 of dtu minus Laplacian of u. So this is gradient of h of u, which I can replace here. And so I will get, as a final formula, I have minus, I don't care because I have a square, 4 sigma of u square, but I have here 1. So this is 1 over 4, 0t, 1 over sigma of u, and then this expression. Gradient minus 1 of dtu minus Laplacian of u square. Okay. And this gives me a formula which depends only on u, right? You don't have h anymore. So this formula, it's okay, and that completes. So we proved the lower bound, modulo some technical obstacles, and we have formulas for the rate function. 3 different formulas.
For this last one, you are using the fact that your u is away from 0 and 1.
Yeah, so
So they are not always 1, because here you are asking more.
you have to give a sense to that. Okay. It has a meaning if u it's very nice, bounded away and smooth, right? Because here I'm taking the derivative, I'm taking the Laplacian. But in general, you can make sense of these things. In some sub-LF spaces, you prove that u has, it's differentiable in the weak sense. If it has if I it's finite, the fact that the rate function it's finite gives you some information about the trajectory. In particular, that it has some smoothness in space, and you can use that to make sense to this formula. But it's a formal formula, right?
So what I'm concerned is when you divide by sigma, if you're not.
No, because you see, this is L of u. It's telling you, I know that this is finite. I know that this linear functional minus this one, minus this quadratic expression, it's finite. So this is telling me that that the function u, so what is appearing here, when I take, it's like a Schwarz inequality. It's telling me that 1 over sigma of u will be finite. So the integral of what I, okay, so let's come back here. All right. So I know I'm taking a trajectory I for which I of u is finite. Okay? So I know that this supremum is finite. All right? Fine. Now, this expression here, it's defining Sobolev space. So I'm defining now, I'm taking two smooth functions, h and g, and I'm defining a scalar product between these two smooth functions as the time integral, the space integral of what it's written over there. Okay. So let's take smooth functions, defining the torus times the time, define this scalar product, then declare two functions equal if the difference of the norm is equal to 0, because if sigma of u is 0, this scalar product can be 0 even if the functions are not 0. Right? So declare them equivalent if the scalar product or the norm of their difference is 0, and then complete this space. And then you get a Hilbert space in this way. A Hilbert space which is induced by this scalar product. Now you have here a linear function. And what this variational formula is telling you is that this linear functional, it's a bounded linear functional in this space. If it's a linear and bounded, then you know that by Riesz representation theorem, you know that there exists one. So there exists my HU, another way in which I can make sense of H of U, such that LU H or LU G, it's equal to sigma U dH U dJ for all j. Okay? So this is an abstract way in which I can construct this function. And so I know that I just proved to you that for any u, without any hypothesis on u, there exists an h in some strange space, well, strange, in some Sobolev space, which satisfies this identity. And this identity is exactly the one which tells you that h solves this equation. Okay? So this type of argument will allow you to actually prove that these formulas for general functions u. Because you can extract information from the fact that the rate function is finite. Right? Other questions? So what I hope is that you have an idea of how to prove large deviations for these models. You know what are the main steps, what you need to do in order to prove the upper bound, and then how you prove the lower bound. Of course, we didn't go up till the last detail because we had no time, and that will be quite boring. There are many technical details in the road, but I hope that you have a general, a clear idea of what is the strategy you need to follow in order to prove. And what's interesting is that, as we showed, that this strategy is essentially the same in very different contexts. Okay, so with that, that was the last lecture. So, well, I hope you learned something. Okay, so bye-bye. See you next semester.